Okay, so we have a vector field f. We want to compute the circulation of f around C1. That's just this bottom thing here. This is just another word for the line integral of f around C1. Okay, so and notice that it might be hard to see, but I am saying that it has the counterclockwise. Notice that I'm saying it has the counterclockwise orientation. It might not be easy to see, but that's what this arrow here means. And then I also put the arrow there. Okay, so we're given these three pieces of information along with some measurements. These circles C3, C2 have radius 1, and the circle C1 has radius 5. So what can we use? So this is a Green's theorem / Stokes theorem question. So one way to write Green's theorem, so I talked about this in one of my videos. So if you have I talked about this in a previous video. If f is a two-dimensional vector field, PQ, we can make it a three-dimensional vector field just by adding a 0 component. And now we can use Stokes theorem. And if we do Stokes theorem, this is one of my previous videos, we can write it in this way: the integral over the region R, curl of f, the z component of the curl of f, dA. This is equal to the integral over the boundary of R with the positive orientation f dotted with ds. Okay, so the z component of the curl of f, where now I'm thinking about f as being a three-dimensional vector field where the third component is just equal to 0. The curl of f, the z component of the curl of f, I do that integral over the region R. This is equal to the line integral of f around the boundary of R with the proper orientation. So how can we apply that to this particular problem? Well, so what we know then is the integral over the region R, the z component of the curl of f, this is 5. Okay, so this is equal to the integral over the boundary of R, where this is the region R here, f dotted with ds, the line integral of f over d around the curve. Okay, so now the boundary of R has three components: the C1 curve, the C3 curve, and the C2 curve. Because the areas, these gray areas here that are enclosed by C3 and C2, those are not part of the region. Okay, so this is equal to the integral over C1 with the counterclockwise orientation of the vector field f. Now that's what we care about. Okay, this is the thing that we want to know. Now we have to think about the integral around C3 and C2. So notice that the orientation of C1 is a counterclockwise orientation, but notice that since C2 and C3 are inside the region, that has counterclockwise orientation. So this is going to be plus the integral over C1 has counterclockwise orientation because it is the outside boundary of R. C3 and C2 are the inside boundaries of R, and so they have clockwise orientation. And I explained this in one of the videos on Green's theorem. Okay, so what is this? Well, C1, this is the thing that we care about. Okay, so now let's look at the other pieces, some of the pieces of information we have. We know that the line integral of f around C3 with counterclockwise orientation is equal to 9 pi. So then the line integral of f around C3 with clockwise orientation is minus 9 pi. And similarly, that says C4, but that should be C2. And similarly, the line integral of f around C2 with counterclockwise orientation is 2 pi. So with clockwise orientation, it's minus 2 pi. So this is minus 2 pi minus 9 pi. Okay, now what about this? So basically, this integral is just going to be 5 times the area of the region. So what is the area of the region? The area of the region, so it's The area of the region is the area of the big circle, which is 25 pi, minus the area of the smaller two circles. Well, the area of each of the smaller two circles is pi because they're unit circles. So this is minus 2 pi. Okay, so this, the thing that we care about, is going to be equal to 5 times 25 pi, 5 times 25 pi minus 2 pi plus 2 pi plus 9 pi. Okay, and all I'm doing is I'm just solving for this by adding the 2 pi and the 9 pi to both sides. And you can simplify this and see what it should be. Well, actually, I can just do this for you. So this is 125 pi minus 10 pi. So that's 115 pi, 126 pi. So if I added this part together correctly, it's 126 pi. And sorry, this video might seem clunkier than others. I don't know what's going on, but my Apple Pencil keeps disconnecting from the iPad and it's driving me crazy.